thanks. I think you guys are going to be happy because I'm not going to talk about codecs. Wow. No. Who'd have thought? All right, so I'm going to talk about something called the Media Communications Mesh. This is an open source, scalable media transport framework that we released into open source around September, October of last year. And you can go, get it, grab it, play with it, do whatever you want. And I'm going to tell you about it. So first, let's talk about the environment that this framework would naturally operate in. So consider an application which I think is representative of a lot of the discussions that have happened over the last couple of days, where you have applications that span the cloud through some kind of edge environment. Could be Kubernetes, could be some other orchestration system, even manually orchestrated environments, and then some equipment that's on-prem, camera equipment that you're connecting via some form. It could be an extended LAN, it could be a completely separate network. And what the Media Communications Mesh does is it makes no assumption about the types of networks that exist between these environments. Okay. So, so that's sort of the environment. And we essentially provide two kinds of services inside the Media Communications Mesh. We provide a media transport engine, a data plane, and we provide some very low-level control plane support. Let's call it that. And I'll tell you about it. Okay. So first, let's talk about the data plane. So what are the goals of this type of data plane? We want it to be very scalable. We want it to be high bandwidth, low latency, reliable, secure, which I haven't even listed, but yes, security is very important. And in my opinion, as abstracted as possible from the application. So the applications shouldn't have to consider media transport at all. They should only think about, I receive a media buffer of some kind, and I write a media buffer of some kind. That's it. There's nothing else. Okay. And okay, so then the next part is that control planes are arbitrarily complex. They're real beasts. And what we want to try to do there is create some abstraction layers, but not like we're going to replace NMOS or anything like that. In fact, we want to exist well below that level. And I'll talk about that near the end. Okay, so this Media Communications Mesh is, the data plane is based on the Media Transport Library. Quite a few of you are familiar with it, and some of you have used it and are deploying it in your products. It's a very mature library. It's been out for a couple of years, completely open source. Take it, do whatever you want with it. If you'd like, call me when you're using it. I'd love to know what's happening with the library. It is completely unrestricted open source. So Intel doesn't make any claims on it. We want you to take it. We want you to port it to ARM, port it to whatever you feel like. It's fine. We just want to learn from you. Okay. And this media transport library, just do a quick overview of it. It has two brand new network stacks. The first one is an ultra-low latency, POSIX compliant, UDP-based network stack. So DPDK traditionally had, for the last 10 plus years, probably 15 years, has supported TCP very efficiently. But I think if you guys have done any work on UDP, and I'm sure a lot of you have, the OS UDP stacks are horrible. There are unpredictable latencies, long latencies, all kinds of other problems. And DPDK didn't even have that. So we went out to the world and said, hey, does anybody have an efficient UDP stack? And nobody in their right mind goes and develops a brand new UDP network stack if you don't have to. Well, we had to. So we did. So we developed the UDP stack. It's now been widely tested. It's all over the world. And on top of that, we developed a complete RTP stack because we wanted to support things like ST2110. And we also, being the masochists that we are, implemented a complete ST2110 solution. Completely open source. Take it, play with it, have fun with it. Use it in your products. We would love that. In addition to the protocols that we've developed, we've also validated third-party libraries. In particular, we've validated RIST, which I think should be great for you guys here, and we have validated Quick, in fact, several Quick libraries, including the official Quick library as well as Pico Quick and a couple of others. And you know, we're kind of not really in, we're asked not to talk too much about the future, but I'm going to say that IPMX is very important to us, and we are exploring ways to, you know, see if the Media Transport Library can support IPMX. You can read whatever you want into that. It also has some control plane capabilities. We created a brand new ultra low latency, low jitter, excuse me, PTP stack. It also happens to be ultra low latency. It's plus or minus 50 nanoseconds accuracy, depending on some hardware assumptions. If there's absolutely no hardware assumptions, I think you can still get within plus or minus 100 nanoseconds. And then we support ARP and IGP. Okay, so that's the Media Transport Library. And the library is fine, it's great, it works, wonderful, but what we really are thinking about is cloud native, scalability, and most of all, virtualization of functions, right? We love things that operate in abstracted compute environments. And so the more we can virtualize workloads, you know, the happier we are as Intel, and we hope the happier you are as well, with the flexibility and the power and the scaling of the technology, you know, Moore's law and storage and networking and all that. So, so the first thing we thought of is, okay, great, let's just use you know, Envoy, Istio, and we're done. It's great, wonderful. Yeah, no, that doesn't work at all. Not even a tiny little bit. And the problem comes down to the assumptions under which both Kubernetes and service mesh systems were designed. They're really designed for ephemeral services, and really ephemeral. Like, they're up for minutes, perhaps small hours, maybe. They're really designed for transmitting data between them, and generally quite bursty types of data. And for media transport, we want really long-lived services, days, perhaps weeks long, right? You don't want your, you know, Olympics to go black, right? Stuff like that. And we want it to be very high bandwidth, very low latency, and most of all, continuous. And when you try to do this with traditional service meshes, it just doesn't work. So what we did was we created a different architecture, and I'm going to dive a little bit deeper into that architecture. But there's a nice little, very summary picture, but I'll talk to you in more detail. Okay, so here is the more detail. So what we want to do is, let's ignore the control side for a moment. I'll come back to it. Let's talk about the data plane. So the first thing we want to do is that high level of abstraction. And we want an environment where it is extremely efficient. So we can't be making all kinds of copies of uncompressed or lightly compressed video, or our cache, you know, coherency, and, you know, just goes, it explodes. And we have all kinds of problems. Even very small number of streams, when you start duplicating them, if you're doing 4K, 8K, it's a mess, really bad. And so we wanted everything to be zero memory copy when you're passing media between containers and between those containers and the NICs when it has to go to another server node for processing. So we created a Kubernetes daemon set that acts as the proxy. And so it services all of the containers in that particular server node. And if you guys know Kubernetes, you'll know that this is not exactly following the fundamental principles of Kubernetes, where you want everything pretty much to be, no shared, namespaces and all that kind of stuff. So we had to find a way to solve that problem. The good news is we didn't have to. There was already a great solution, in the industry, and I have to thank Cisco for developing, the FIDO VPP project, releasing it to open source, and so we're using the MEMIF interface specification in FIDO VPP, and we've done some extensions to it and contributed those back, and we can actually do memory buffer pointer transfers and being able to do that between arbitrary containers, arbitrary pods, and on the same server node and down to the NIC. So it's great. So that works beautifully. We also, in certain compute environments, we can take advantage of DMA acceleration, and so we can even completely offload any kind of media transport away from cores that our customers are buying to use for their compute load. So they don't want to use cores for overhead. They want to use it for their application. So that's what we do, is we try to abstract as much of the communication away from the compute loads. Okay, the control system, I'm going to talk in more detail towards the end. That's much more conventional. You can use Envoy, you cannot use Envoy, you can use Istio or not, you can use your own infrastructure. We have some recommendations, and we have some infrastructure that is being implemented, and I'll talk about that. Okay, so when we put all this together, you're going to have a control plane with implementing some specific media controllers of your choosing, either your own custom control plane, or you're following some standards. It might be ONVIF if you're in the IoT world. It might be NMOS, the most likely candidate for this audience. It could be the WISH project from WebRTC for WIP and WEP. It can be others. There's not a huge number of standardized control planes out there for media, or for anything for that matter. But there are a few, and NMOS sure is a great candidate. I'll talk about some of the problems with NMOS later when we go into the control plane in more detail. In terms of the data plane, we've already talked about that. So once you have passed all of your graph node configuration in some form, like STP files, for example, and you've connected everything, then you can start generating your flows across all of these nodes. So now I'm going to jump into the architecture of the media proxy itself. I'm not going to spend too much time on this because I really want to get to the control plane side. And by the way, all this is in the code. You can read about it. There's papers that have been published, ACM. You can read about the media transport library and media communications mesh. So the functions that we provide in the media proxy include NCAP and DCAP. We provide packet pacing, either very accurate, like for ST2110-21, or we can also provide looser models for other environments. Certainly we can do narrow gap, narrow linear, wide, and some others that are just rate limited packet pacing models. We have a codec plugin API. You don't have to use it, but if you decide it's an arbitrary API, we don't distribute codecs. I said I was going to talk about codecs, so I'll stop that. Okay. One thing that is really cool, and it's in the media transport library, so therefore it's in the proxy, is we provide a very rich library of format converters for video, and they're highly optimized, and so. That's one of the reasons why some people grab the media transport library is just for those format converters that my team developed. So take a look at those. They're really cool. They're incredibly optimized, and they're optimized for a number of different platforms. So not just it won't just work on Intel. It'll work on a number of platforms. It's pretty universal. We have packet protocol processors inside for all the protocols we talked about earlier, and we do session management. So it has some control plane capabilities, but it's passive. It expects to receive configuration information because the media proxy has to know if I'm acting as a proxy for some pod on my server, I have to know when that flow comes into my IP address that I need to then do something with that. I have to take some specific MEMIF channel and pass it onwards. So there's some configuration that you have to go through, and we do some abstraction of that, and I'll talk about that in a moment. All right, so actually we're going pretty fast, so I think we'll have time to go into the control plane a little bit. I do want to say everything I've talked to you about until now is released, it works, and it's available to play with. This next discussion is some, you can say, thoughts and ideas that we're playing with. There's no promises that we will develop with, when, how, anything like that. But you know, that's just part of Intel rules, I have to tell you that. Okay, so let's talk about control plane. So imagine that you have an application, and it will define your connection graph, right? It knows who wants to talk to whom. It makes decisions about where it's going to locate the device registry. The device registry can live in very different environments, very different networks, completely, could be on the internet, halfway around the world if you wanted to. Probably not, you don't, but it can be. So it can be DNS accessible. You might want to translate, MDNS multicast, but you don't want to do that and can't do that in AWS, right? So if you're in that situation, you want to use some kind of translation systems that will allow you to map certain services between them, and I'll talk a little bit about those. Okay, so that's your application. From your application world, you only think about the graph you're trying to build. You don't think about how, you just know you want to build something, and you have certain database information that you're going to be distributing, and certain business logic, operational parameters. Then you're going to move into a media controller. And again, this is not part of what we're doing. We're not replacing NMOS. We're not building your media controller. That's completely up to you. You're going to define, your own discovery, your own registration, authentication services. You're going to do, your own device configuration, service configuration, and you're going to do your own both real-time and paced control. So, but there's a problem, and the problem is that you put this media controller somewhere, right? It's often placed inside the Kubernetes cluster that has the services they're using, but it could also be in the cloud, right? There's no reason why it can't be, and it often is. So it can arbitrarily be in the blue or in the yellow area. So the question then is, how do I transparently deliver these configuration messages without having to know all these details about the network itself, right? Are there ways that I can abstract the network environment? And that's what we're working on. So we are building a control messaging system that allows you to transparently translate your commands, your service commands, which are packets that you're sending of information, and allow you to transparently reach destinations without having to know much about how to get there. And so we help you build that with very low-level services. And we do that not only for wired networks, but also for wireless networks. So we rely on a set of, you've probably heard of it as referred to as telecom APIs or network APIs. You can interface to those through our control messaging, what we call the network mapper, through this control messaging system, and then you can interface directly to remote sessions that are coming in wirelessly. So it's a very powerful interface. And this network mapper then allows you to translate your registered devices and maps those into the difference between the network definition of your device world versus your service world, which can often be completely disconnected networks. And so you may create things like, you can think of them as somewhat as like reverse VPN kind of connections, but they're more abstract entities. And so from the point of view of the business application logic and the media controller itself, it's connecting a device in the registry to a device service in the registry and making them communicate, or any end graph configuration they're creating. And it doesn't have to know anything about the fact that these services are spun up dynamically. They're allocated by Kubernetes in some arbitrary server location and that you don't know about in advance. We help you do that. Now, the ephemeral problem that was brought up earlier, sorry, can somebody remind me who was talking about the problem with ephemeral services? Was it Andy? I can't remember. So somebody was talking about the problem that there's no knowledge of time in NMOS registries. And this isn't something that we're solving ourselves. We're not solving the control logic. But what we can do is, if you spin up a service, once that service is live, you can do it completely on demand. So minutes, maybe even seconds before you need it, you spin it up, you save a lot of money. Sorry, Thomas. And then you follow your registration process, and then you follow all of your STP connection process through your media controller, and you don't care and don't know where that device ended up. We will map it for you through our network mapping system that's part of the media communications mesh. Now, please remember, this is all forward-looking, speculative stuff, may or may never happen, but let's say we've thought about it quite a bit, and we would love to get your ideas, your contributions. This project is live. There's going to be code dumps very regularly into the space, often daily, very often daily. So keep an eye on it. So we provide two types of connection services, of communication services. One is the connection services, which do the actual mapping between virtualized services, or you can think of them as virtualized devices, and physical devices that exist somewhere that are already plugged into a network. So we do that mapping automatically. Then the other part is a little more difficult to understand. Let's say that you want to send a message of some form. It can be a configuration message, or a control message, or other types of messages to a device or a service. If you have to know everything about the structure of the message you're sending, all the way down to the packet structure, it forces you into very specific network configurations and into very specific hard-coded protocols. Instead, what if we provide an abstract messaging, low-level messaging network that's just an API, and you just call it. Say, hey, I need to send a control message to this UUID. Please send this arbitrary packet of data to it, and I don't have to worry about it anymore. My media controller doesn't have to think about how to get that message out there. Now, in NMOS world, NMOS is not particularly cloud native. I'm sorry if I'm insulting NMOS people here, but NMOS was designed with a very centralized view of the universe, whereas Kubernetes is scalable, distributed, and all that. So what we're trying to do is bridge those two worlds, right, and make everything as scalable as possible. And so if you think about that, if we were able to give your media controller a sort of an API that's almost like a fictional virtual network connection, and then we take care of all the routing and everything after that, and you don't have to think about it. That's nice, right? It frees up your controller to think about the type of control you want to implement instead of having to think about the networking part. And then so that's one aspect of the messaging. For those of any of you work in IoT world or working with more dynamic camera environments or sensor environments, perhaps in hospitals or other environments, this type of control messaging needs to interoperate with other highly abstracted protocols, like you may be familiar with MQTT or 0MQ and others, right? So what we want to do is let you send your MQTT messages. But MQTT messages are unstructured, so is there a way that we can help you deliver structured messages without you having to spin up MQTT servers and clients, and we can just handle it for you? Well, that's what this is about. Okay. So, and one of the things that may be coming through, and I hope is coming through in this discussion, is that as Intel, we don't try to solve one industry's problem, right? We want to be as broad and general for as many possible industries as possible. And so we're thinking about this as solving network transparency problems in general. And so if you guys are working in video production or in Pro AV world or in other environments, we welcome your input and your thoughts into how we can create APIs that serve you better and help abstract complexities that you'd rather not deal with, don't care about, and worry about your own control logic and your own application logic. Okay. So that's what this is all about. And sorry, I just realized I forgot to introduce myself, so I'll do that because I've got a few minutes. So quite a few of you know me, but my name is Raul Diaz. I'm a senior principal engineer at Intel. I work in one of the 3 big product groups. I work in the network and edge group. And I'm not a networking guy. I'm a video guy, as some of you already observed. But I've learned a lot about networking over the years. And I have teams that work on networking, and I have teams that work on video processing and other things. This is obviously on the networking side of my stuff. I work in the network and edge team in the office of the CTO. So I support multiple business units across multiple industries, which is why I've mentioned some of them. And yeah, so that's me. Okay, we have a few minutes, so that's everything else. I think that's it. Thank you so much.